And I love it, James. Your brain is going good. So I didn't put the curve. I did put the curve, yeah. So there's your curve. Alrighty. This hits here at 2 and it's here at 0. So how are we going to figure that out? How are we going to figure out what those 3 tangents are? You got one here, like you said. You got one here. You got one here. How are you going to figure out? So we got 3 tangents. How are we going to find out those equations? Ideas. Well, first of all,
find the slope.
We're going to find the slope. Yep, we're going to have to find the slope, right? Because we want to know what is the slopes of the tangent line. So first of all, let's find the slopes. And you guys remember what formula we use to find the slopes? You're doing 2 things. I hear, James, what you're saying. Okay, so first of all, there's 2 things we need. Good. I like what you just said. So we're looking to find the slopes of the tangent lines. So the first thing we have to make sure we have is that we have the formula to find the slope. The second thing we need to have after we get the formula to find the slope is we need to find where this is occurring. At what angles, right? At what angles does the curve hit the pole? So there are 2 pieces, right? One piece says, okay, what's my derivative? What's my slope? What is that formula? The second piece says, well, okay, at what angles does this happen? Right? So it's a good warm-up after the weekend. We looked at finding slopes last week. So let's see. Let me just do a quick rundown. We said to get dy dx, we took dy d theta divided by dx d theta, and we came up with this big, huge formula, remember? Because we have 2 conversion factors, x equals r cos theta, y equals r sine theta. And so last time we said, okay, r is a function of theta. That means we have a product rule going on, and we derived last time this formula. We said that's equal to dr d theta sine theta plus r cos theta. See, look back in your notes and see if you don't see this. Dr d theta cos theta minus r sine theta. So you should look back in your notes and make sure that you have the first derivative for a polar curve, r equals whatever. So it should be dr d theta sine theta plus r cos theta over dr d theta cos theta minus r sine theta. That was our formula. And so actually, I'll just keep working this one first, and then we'll go to the second piece. So for our specific curve, r is 2 cosine 3 theta, and dr d theta for this specific curve, we're going to have to use our chain rule, right? I love it. Oh, minus or plus? Minus. Yep, derivative of cosine is negative. We got to pull that extra 3 out front. 3 times 2 times the derivative of cosine is 6. Minus 6 sine 3 theta. So yeah, so r is 2 cos 3 theta. Dr d theta is minus 6 sine 3 theta. And so what we're going to do is we're not going to do that. What we're going to do is we're going to substitute. In place of dr d theta, you're going to put minus 6 sine 3 theta. And in place of r, you're going to put 2 cos 3 theta. And that's going to tell us what the formula is that we can use, or the way to derive the slope of the tangent line. So it's going to be negative 6 sine 3 theta times the sine of theta plus, and then r is 2 cos 3 theta cos theta, all divided by negative 6 sine 3 theta cos theta minus 2 cos 3 theta sine theta. Now be very careful. People, students like to think, oh my God, I see sine 3 theta and I'm going to cancel it. They say, oh, I'm going to do that, but you can't. You can't because they're joined by pluses and minuses, right? In order to cancel things, we have to have factors. So in order to cancel something, you're going to have to be able to factor them out first, top and bottom, and then you can cancel common factors. So don't try canceling anything unless you can pull something out. This would be your slope. If you want to, you could pull out a 2. We could factor out a factor of 2 if we wanted to from top and bottom and cancel that if you want to get a little simpler. But otherwise, that's your slope. So you could take a 2 and pull it out. It doesn't do any, you're right, it doesn't really do any kind of simple. It doesn't really make it that much simpler. Absolutely it doesn't. But
because of the 3 theta, we can't do any exercise.
Correct. There's not much else we can do. So yeah, so I actually probably wouldn't take the time to do that, but if you wanted to, you could. And 1000% get this. Okay. So that brings us to the second piece, which, James, you told me. You said, okay, well, now we also have to find theta. And how do you find theta? It's where your curve intersects the pole, right?
Yes, so R equals 0.
So R equals 0. I love it. God, so smart, so thinking. So you intersect the pole when your radius is 0. So what we could do is set our radius equal to 0. So that means our curve, 2 cos 3 theta, equals 0, which means cosine 3 theta equals 0 divided by 2, or in other words, we're looking for the cosine of 3 theta is 0. How do we solve this? Do you guys go back in time to trigonometry or calculus 1? How would we figure this out?
Isn't cosine 0 at pi halves and 3 pi halves?
Good question. So where is cosine 0? Exactly. So where is cosine 0? It's 0 here at pi over 2, pi halves, just like you said, Andrew. Down here at 3 pi over 2. And then again, right, the first angle would be pi over 2. The second angle would be 3 pi over 2. I could go around my circle all the way, and that would give me 5 pi over 2, right? All these angles. And so actually, that's not the angle we want because we have 3 theta. So really, 3 theta has to equal pi over 2. Yeah, 3 theta has to equal 3 pi over 2. 3 theta would have to equal 5 pi over 2, right? So that's how we're going to get our 3 angles that we're going to substitute in. And you'll notice there's 3 of them, right? Pi over 6, pi over 2, and 5 pi over 6. When theta is pi over 6, the cosine of 3 theta becomes the cosine of 3 pi over 6, which is the cosine of pi over 2, which gives me 0. Yes. That is beautiful. You guys are so smart. Okay, so once you get your formula and you get your angles, then all we have to do to complete this warm-up problem is say, okay, we want to find the slopes at those points. So the last step, which is our third step, is we want to find dy, undo Tina, we want to find dy dx when theta is pi over 6. We want to find dy dx when theta is pi over 2. And we want to find dy dx when theta is 5 pi over 6. How are you guys? Are you guys okay? There'll be some symmetry. There'll be some things that you're going to notice. So how do we do that? What do we do, Drew? We do what? We take that angle and do what with it? Thank you very much. Your parents all must be very proud of you, and you should all be very proud of yourselves. Seriously, you guys are working so hard, studying lots. There's so many other more fun things to do, I bet, than calculus too, but you guys should be really proud. You're working so hard. I'm going to plug it in just like you said, Drew. I'm going to put 3 pi over 6. Actually, pi over 6, but because there's a 3, it becomes 3 pi over 6. Cosine 3 pi over 6. Sine. Cosine. Cosine. Sine. Okay, so what does that give me? Minus 3 times the sine of pi over 2 times the sine of pi over 2 is 1 times the sine of pi over 6 is 1/2. Cosine of pi over 2 is 0, so that second piece becomes 0. Sine of pi over 2 becomes 1. Cosine of pi over 6 becomes square root 3 over 2. Cosine pi over 2 is 0. It looks to me like I'm getting 1/2 over square root 3 over 2, which is 1 over the square root of 3. So it looks to me like the first slope I want is 1 over the square root of 3, or if you rationalize, square root 3 over 3. So that's your first slope. And if I look back up top at my curve, right, that would be this slope of this tangent right here. Slope is 1 over the square root of 3 units. And everybody's plugging in pi over 2. Well, that's 0. That's 0. Are you guys getting at pi over 2 that you get 0 on the bottom?
Yeah.
It doesn't even matter what's on top. You're getting 0 on the bottom, which means your slope is undefined. So for the second one, your slope is undefined. And what I really love about math is, right, our algebra, all of our work should match our picture. And remember what the picture is. It looks like this, right? It's this 3 curve. So right here at pi over 2, we've got a vertical tangent line. We've got a slope that's undefined. And I'll just leave it for your notes. We don't have to do it now. But that third slope is the slope that comes down. And because of symmetry, what you're going to discover, and I'm just going to say leave it for you to finish. But if you did the first 2, you'll be able to get the third one. But what you'll discover is that third slope right there, that the slope there should be negative 1 over square root 3. But that gives us the slopes of the 3 tangent lines to our curves. So we have one that goes positive. Slope is 1 over square root 3. We have one here that's undefined. Slope is undefined. And then we have a third slope that goes down right there. And that one has negative 1 over square root 3. So to recap, to get the slopes of tangent lines, we use our formula, dy dx, which is very special with polar curves, right? It's a big, massive thing. Then we find angles, and the way we do that is key. We find, in this case, where we hit the pole, so we set r equal to 0. And then the last thing we do is we take dy dx, and we plug in those angles that we get. I want to put a note on the board while you guys are copying. R equals 2 cos 3 theta. I'm going to come back to this hits the pole at theta equal pi over 6, theta equal pi over 2, theta equal 5 pi over 6. We'll see. Hopefully we get to this by the end of class. I'm not sure if we will, but I'm going to try to get back to this problem at the end of class. A problem using that, so I'm going to put that on the board so we have that information for us. So that brings us to our topic for today. We're going to spend a lot of time on this. Area of a polar curve. And so I think it is very worth taking the time to talk about how we get the area of a polar region from scratch. And so I want to go back in time very, very quickly. And I want to put a curve F on the XY plane. And if I wanted to find the area under this curve, we used calculus and we came up with an integral. But that integral was based on dividing our curve into what? Our area into what? Small rectangles. Thank you, James. Absolutely. So what we did was we approximated the area of the curve by taking lots of rectangles underneath it. But then what did we do with the rectangles? We shrunk them. We made the width of each rectangle go to 0. So we had a couple symbols. We had this delta x, which described the width of each rectangle. And we had this guy here, which is a rectangle. So we looked at the area of the rectangle, which would be the height times the width. We added up all of those rectangles. And then we took a limit as those rectangles shrank, right? And so what happened was we got infinitely many rectangles. We shrank the area. And when we did that, that became, and we defined it to be the integral of the function with respect to x. And so when I set it up like this, you see where dx came from. Dx came from that delta x, and my function came from my function, and together f of x dx was the area of a single rectangle. So that's where our area formula, finding the area underneath a curve, comes from. Okay, areas of rectangles. That's in the rectangular plane. In the polar plane, it's not that simple, because in the polar plane, right, everything is based on the pole. And when we talk about an area with respect to the pole, we're talking about the area of a curve. Our curve goes around a pole, right? And we're talking about taking an area between the curve and the pole. It's not as clear cut. So when we have an area, it's a different kind of area. Yeah, so instead of cutting it into rectangles, we are going to cut that area into wedges. I like what you just said. A wedge. It's also called a sector, right? A sector of a circle, but I like the idea. It's a wedge. And what's the area of a wedge? Well, it's the area of the whole circle, which is pi r squared, right? It's the area of the whole circle. But the wedge is just a piece of it, a proportion of it, a fraction of it. So to get the fraction, you take the whole thing divide it up by 2 pi, and then multiply, because if you take the whole thing, divide it up by 2 pi, that gives you 1 radian, but then multiply that 1 radian times theta. And so what happens is you're going to discover that the area of a single wedge can be identified with this expression right here, 1/2 theta r squared. And these notes are in Canvas. You can pull them up, okay, download them. I just updated them again last night, like really early in the morning. So you can always, or you could pull up. But this description of how this occurs and getting the wedge is in your notes. And so what are we going to do in summary? We're going to take not just one wedge, but we're going to add up all our wedges together, right? So we're going to take all of these wedges. We're going to add them up just like we did for, going to add them up just like we did. So we have 1/2 r squared theta, and that's, slow back. I'm going to go back to my picture. I have 1/2 theta r squared. That's the area of a single wedge. I'm going to add up all those areas. 1/2 theta r squared. But theta, remember, is like x. It's changing. My angle, what I want to do is take one wedge, but then shrink it down. And so because we don't have an x to shrink, we have theta to shrink. And so what I'm really doing is I'm taking 1/2 r squared times that change in theta, and I'm going to add all of those up and shrink theta to 0. So then I'm going to take the limit as that change in theta goes to 0. So you can see this is setting me up for an integral, but the integral is going to have this. It's going to have a d theta at the back end and a 1/2 r squared in it. And so if you look in your notes in Canvas, you're going to see it right here, and I'm going to put it, I like to use, instead of f, I want to just replace f with r, and I'm going to need to do that in my notes. But you're going to use this formula. The area of a polar curve where theta ranges from A to B is 1/2 pi, nope, no pi because that canceled, sorry, 1/2 r squared d theta. That's the formula you want to have in mind to find the area between a polar curve and the pole. One half r squared d theta, with bounds for our range being on theta, so we're going to go from A to B, or often what you will see is alpha to beta. Often when you talk about angles, you kind of put the limits in terms of alpha and beta, and I like to do it that way because I think that helps me a little bit more, remembering that it's angle measures and not x measures. So how could we do a problem like this? Let's set up an integral to find the area inside one petal of the rose curve. What do you think?
You could fit all that in plus minus 3, plus minus 45 like this wedge. Right.
Oh, what can we fit in between?
Yeah, that's the first question. Fit between.
So the first question is, what does it fit between? We know it hits the pole for the first time at pi over 6. Because actually, if you look at the curve, x equals r, or r equals 2 cos 3 theta. If you look at the curve, r equals cos 2 3 theta. We have an r and we have a theta. It hits the pole at pi over 6, it hits the pole at pi over 2, and it hits the pole at 5 pi over 6. When is it here? It's actually here. So what you'll find is that when you're at 0, you actually have a radius of 2. So actually right here is when theta is 0. Right here is when theta is pi over 6. And this curve, remember, polar curves are like parametric curves. They're tracing points, and it's moving. It's kind of like a movement, even though we don't have a parameter that moves. You can think of it that way. And this point is going around the curve. And so when you're all the way back here again, that happens when theta is pi over 2. And then it keeps tracing, right? And then you're going around your curve, and you're going around your curve, and you're back here again when theta is 5 pi over 2. And then we're tracing, and we're tracing, and we're tracing. And if you look in Desmos, you'll see that you get back here again when theta is pi. Polar curves are like parametric curves in that they kind of move over time. That's the idea, because theta is tracing around a clock, or theta is tracing around time as you go the angles. So it's really neat the way it works out. So if I want to find the area inside one petal, you're right, James, I could find the area. So let's say I wanted to find between pi over 6 and pi over 2 and use those as my limits. That actually, weirdly enough, would give me this area in here. So one way to get the area would be to use the limits pi over 6 to pi over 2. And then our formula up top, which is 1/2 r squared. And r squared is 2 cos 3 theta. And so this right here would be an integral that we could use to find the area of that petal. Other thoughts? Because that's not the only way. The nice thing about polar curves is there's actually, because of the way the polar curves behave, they're periodic, right? There's lots of ways to define or describe one petal. Other thoughts? How else could we write the area?
Do you like 2, and then do you like the upper half of the first one?
Yeah, we could do 2. Let me put this one in green. We could go 2 from 0 to pi over 6. Absolutely. So we could go from 0 to pi over 6. And if we were going from 0 to pi over 6 and doubling it, it would give us 2 of those. Yes.
Cancel from the 1/2 and 7?
It would. Yes, it would. Yes, it would. Yep. But that would be a second way that we could find that area. Absolutely. Other thoughts?
From theta 0 up to the midpoint of the next one.
I could go from 0 to, if this is pi over 6, what do you think the midpoint is here between pi over 6 and pi over 2? I think it's 3, so it's 30 degrees to 90 degrees, right? So 30 degrees to 90 degrees means it's 60 degrees. So yeah, you could go from 0 to pi over 3 and get that much, because that's 2 halves, and put it together, right? Another way you could do is you could take the entire curve and divide by 3. And it takes, actually, we have to go from 0 to pi. If you look on Desmos, 0 to pi, well, I just told you, from 0 to pi, it gets you all the way around. If you divide that by 3, it would also give you the area of one of the curves dividing by 3. So take the whole area and then divide by 3. So there are lots of ways that you can find the area of a single petal. Different ways you can set up your integral to do that because of symmetry, because of the way polar behaves. This is where students sometimes get way confused and they're like way overwhelmed. And in fact, I overwhelmed my class this morning. I just overwhelmed them this morning. I feel bad. But there are lots of ways to do this. Pick the one that resonates with your brain the best. And if you don't have one that's the best, my suggestion is to always figure out where your curve is intersecting, in this case the pole, and take 2 limits that are next to each other. That will always give you the safest way to get an area between those 2 angles, okay? Any questions? Any questions at all? Do you see a lot of applications for this? Windmills, once we start spinning it, moving things. What's the surface area of a windmill? How much wind do we need to make it turn or think? You know what I mean? There are so many applications for these kinds of things. Fan motor, all kinds of cool stuff going on here. All kinds of cool stuff. That's how I should start the class, huh? We should start some physics problems. No, thank you, no. Thank you, no. We'll just stick to the math behind the physics. And say, picture this as a windmill. Picture this as a fan motor. All right, any questions on that first problem? Let's look at problem 2. All right, so this time, instead of just finding the area in a petal, I want to make it a little more complicated. And I want to find the area inside a petal, but outside the circle. Inside the petal, but outside the circle. So the first thing you have to do is figure out, right, what area am I talking about? So that's the first thing. So what area are we talking about, guys? We're talking about the tips of the petals, right? We're talking about the parts out here, right? That's inside a petal, but outside the circle. So we're looking at these areas here, right? But we just want one of them. So let's talk that through. If I do 1/3 of 0 to pi, it will give me one entire petal. Okay, so let's talk this through. So if I was going 1/3, 0, let me color this, coordinate this. If I was going 1/3 0 to pi of 2 cos 3 theta squared with a 1/2 in front, that would give me the area of one petal. But we would want to, we need to subtract out this piece right here, right? So we would want to take out the inner piece. So we'd want to subtract out the inner piece from that. So how much am I subtracting out?
So that'd be -1.
This is not an easy problem, right? So yes, your radius is 1. Your radius is 1. It's not a complete sector, though, so I can't just take a fraction of a curve, right?
Yeah.
Because it's not straight. These petals are doing this.
Would you have to find the intersection?
so we would have to know, and it would behoove us to know, where are those two curves intersecting? Because if we know where those two curves were intersecting, that would then give me my angle measures to integrate, right? So there's a lot of ways to do this problem. I love what you're thinking, and I'm going to put all of this here into a think. This is where we really got off tangent this morning, because this problem can be thought of in a whole lot of different ways, right? And everybody's brain is going to go a different way, and we could explore all the different ways people's brains are going. But I like what you just said, Andrew, because I think this is one way that we can all kind of go together at the same point, which is really what we could do is find intersection points. We want to know at what angles are these curves intersecting each other. And if I want to figure out where these curves are intersecting each other, what do I want to do? How am I going to do that?
You know r equals 1, so you can just set 1 equal to 2 cosine 3 theta.
Thank you. To figure out where they intersect, set them equal to each other. 1 equals 2 cos 3 theta. 1/2 equals cos 3 theta. So we are trying to figure out, where does 3 theta equal 1/2? Ooh, so where is the cosine equal to 1/2? The cosine is equal to 1/2 up here and down here and every other multiple of it. So 3 theta would have to be pi over 3. Or 3 theta would have to be 5 pi over 3, etc., right? We could do the plus pi k, plus 2 pi k, all that kind of stuff, but for us, we're just going to say, okay, theta could be pi over 9, theta could be 5 pi over 9, etc., right? So I'm guessing theta is 5 pi over 9, right, or pi over 9 right here. Then it's pi over 6. Then it's 5 pi over 9 down here, etc., etc., etc. So what I'm going to do is I'm going to say, okay, here we go. To find the area between two curves, we're going to have to find limits, okay? And the limits are going to come from intersection points. So alpha and beta should be intersection points. Or something like that if we're going to use some symmetry. And then what we're going to do is find the area of the outside curve squared with 1/2, right? Because that's the area for the outside of the curve. And then we're going to have to subtract from it the area that we're developing from the inside curve and square it. And when we put that all together with respect to theta and integrate all of that, that's going to be the formula that gets us the area between the two curves. We're going to have to figure out where they intersect, integrate from those points, and then take 1/2 times the outside curve squared minus 1/2 times the inside curve squared. And for our particular problem, because of symmetry, if I want, yep, we could either do negative pi over 9 to plus pi over 9, or like you said, James, we could go 0 to pi over 9, but double it, right? Double it. We're going to have a 1/2 times the outside curve squared, 2 cos 3 theta squared, minus 1/2 times the inside curve squared, 1 squared. That will give us the integral, or the area between, or the area shown, right, between the curve r equal 2 cos 3 theta and that circle.
I'm kind of,
Confused a little bit. Yeah, tell me, Max, where's our confusion?
so our outside curve
Yes.
is the red, right?
The outside curve, yep, is the red, is the, actually for I kind of wrote over it, but the outside curve is actually this blue curve, right? That traces around, okay? So the outside curve is this blue curve, okay? Good.
So then our points, right?
Yes.
Wouldn't we want to go like all the way over to the right to get all of the petals?
Yes. And so actually right here, if you look right here to get all of this petal, this is when theta is 0. So if we go from theta being 0 to theta being pi over 9, that will give us the top half. If we go negative pi over 9 to plus pi over 9, that gives us that whole part of that petal right there. It's not going to give us this part here. It's just going to give us this part, but it's going to do it. Remember, it's in reference to the pole. So it's actually what it's actually giving you. So what it's actually giving you, if I was looking at it, it would be giving me. I'm gonna. This is really good. It's giving me this area in here, right, with this where this curve hits. It's giving me this part in here, but it's missing these. It misses those 2 little spots there that I would have to keep going. Do you see what I'm saying? I don't know if this is answering your question whatsoever. But to get from 0 to pi over 9, if I'm finding it's giving me like an ice cream cone shape of area. That's if I just take this outside curve squared from 0 to pi over 9 and double it.
Okay.
Then I want to take off from it that inside circle part, which is the sector of that circle. So when I remove that inside part, right, so now from that, I want to subtract from that this part in here, this sector part. And that's what's leaving me with that extra part, that extra out. I know my picture's not at all good, but that's what's leaving me with this extra part on the outside. So I subtract off that petal, this part here, and that's what gives me that outside piece that I'm looking for. Do you see that? We can't go all the way to pi over 6 because then that gets this part, and I don't want this part. I guess we could, huh? Well, no, because then the sector would be catching this extra stuff that's outside that petal, right? If we subtracted that sector part. Do you see what I mean? So if we look at this, so...
I think maybe I'll ask you this question. We can
Oh.
talk about it.
Okay.
Make that easier.
Okay. Did you have a different question, though? I went off.
No,
tangent.
I'll explain it later.
Are you sure?
Yeah.
Okay. Positive.
I'm okay.
Okay. Sorry, I interrupted you.
No, it's okay. It's fine. It's just, no, it's good. It's good.
Let's do another question. Let's do another problem and see if it answers your question, because I think I misunderstood your question. This guy right here. I want you guys to figure out, set up an integral to compute the area inside the cardioid, but outside the circle of radius 1/2. Inside the cardioid, but outside the circle, radius 1/2. And I'm just going to write down as when we have the area between 2 curves, remember we have an integral with bounds, and those bounds are intersection bounds, right? Alpha and beta are intersection bounds. And our formula would be 1/2 outside curve squared minus 1/2 inside curve squared. d theta. Okay.
So why would you not just do like the? I was confused. Like, can you just find all?
You
of
could find
that?
all of that,
Mhm.
and then we'd have to subtract this funky shape underneath.
Yeah. Is that tricky to subtract that funky shape underneath, or what would you do?
I would go, it's.
That's what I was thinking. Like, like I was trying to do that one. I thought it didn't like make any sense.
Now you're stumping me. So if we found all of this area. And then the center of the circle. It's gonna leave us that extra piece. Oh, I think I know.
Yeah, I can't.
Let me think that through a while. Take the area of the whole thing and then get rid of that other piece. But that's a straight line if we just integrate the circle itself. Oh, no, because from 0 to pi over 9, you're right. We have to be very careful. If we got the whole pedal, yeah, we could possibly do an arc length problem. Because you see the whole problem is it's curvy,
Yeah,
right?
so we can't make it.
So if we actually found the whole pedal,
Mhm.
to get that extra piece in there would be almost, I don't know. I'd have to really figure that out.
Okay. This way is easier.
If we go this way, we get the intersections, then we know it's within that range for both of it. So you're getting an ice cream cone shape instead of getting the area of the whole thing. We're actually getting the ice cream cone shape.
Okay. I think it was these would make me confused with it.
They are. Those things always get people. So try it here and see if it makes it a little clearer.
Okay.
So you want to figure out where do those, this one's actually a little easier. And I see in my notes, I think I want to put this one at the very back end because it's a little more complicated than any problem. But on this one, you want to find the intersection points. When does 1 minus cosine theta equal 1/2? Okay. Did you get some intersection? Oh, I'm sorry. Did you get some intersection points for me? Pi over 3 and 5 pi over 3? Awesome. Once you get your integral, I want you to actually go through and evaluate it, okay?
How do you decide what you're?
So you want to set your curves equal to each other. Good.
So you just do it.
Set it equal to, yep, and then take those two values. Yes. Or you could pull that 1/2 out front too. So I wandered and I saw, and you guys were getting, to get your intersection points, you set your curves equal to each other. 1/2 equals 1 minus cosine theta. And so you got the cosine of theta is 1 minus 1/2. So you found the places where the cosine of theta is a half. And if you look at your unit circle, cosine theta is a half at two places, pi over 3 and 5 pi over 3. And so that means as I'm tracing my curve, the first place they hit is here at pi over 3. And then as I'm tracing my curve all the way around, and my circle all the way around, they connect again at theta equals 5 pi over 3. Now there's also symmetry that we could use if we wanted to, but if you find the bounds, you know you can always use those bounds. So when you set up your area, you should be going from pi over 3 to 5 pi over 3. I'm going to pull out the half, and then I'm going to put my outside curve squared minus my inside curve squared.
Can you also do plus or minus pi over 3?
I'd be careful with that, James, because I think let me see, because if I go plus or minus pi over 3, I think, and I have to do it to be sure, I think I'm getting this part in here, but the negative of it. You see? Because I think I'm getting the area between these two curves, but the negative part of it. Do you see what I'm saying? Yeah, so I think you need to actually go the other way. You could go pi over 3, and I think halfway to 5 pi over 3 is pi. So you could take from pi over 3 to pi, which is a nicer angle to work with, and double it if you wanted to. Max, do you see that? Do you see how you got those? Yeah. Down here, how we got those down there.
Yeah.
And let me just put a mark down as you're evaluating. 1 minus cosine theta squared, you have to expand it. It's actually a binomial square, right, guys? So we have to take 1 minus cosine theta times 1 minus cosine theta. So make sure you get that trinomial there, 1 minus 2 cos theta plus cos squared. And let me do one more step here. 1 minus a quarter is 3/4, right? So that's actually taking the antiderivative of cosine squared minus 2 cosine theta plus 3/4. Ooh, and how are you going to evaluate that sucker? Oh my God, all of our integration techniques go out our head, right? Our brain, because you're like, oh my God, Tina, we just rotated things, and then we did parametric, and now we've got these polar curves. What do you do, Drew?
Well, can't you just separate them?
We can separate them. Absolutely, I would separate them. I love your brain. I love that brain. And if you separate them, then how are you going to integrate cosine squared?
Well, can you just change cosine squared to?
Thank you. We absolutely, Andrew and Max, can change cosine squared using power reducing.
1 minus sine squared then. And then we can just-
Actually, it's 1 plus cosine 2 theta. 1 plus cosine 2 theta. Yeah. It's been a little bit of time, right? It's been a minute, as people say nowadays. A is 1/2 from pi over 3 to 5 pi over 3. 1/2. Like you said, Drew, because they're all added, we can separate them and look at them separately. Actually, I think I'll do it that way. I think I'll multiply that in. So that's 1/2 plus 1/2 cosine 2 theta minus 2 cosine theta plus 3/4. And then d theta at the back end. And then you can integrate, right? 1/2 theta plus 1/4 sine 2 theta minus 2 sine theta plus 3/4 theta from pi over 3 to 5 pi over 3. I'm going to wander, see if you guys are doing it. Have any questions?
Did you
Yeah,
think you should distribute the y-half then? Did you distribute
I
Yeah,
did.
but is it-
I
think you should
did.
use cosine theta?
I did. I put the 1/2 in because what happens, and I observe it on tests, is students see that 1/2 and they pull it right out. And you have to be careful because it only applies to this part. It doesn't apply to the other parts. So I wanted to put it in so we didn't get tempted to pull it out. 1/2 and 3/4 actually gives me 5/4 theta plus 1/4 sine 2 theta minus 2 sine theta. So that's what we're going to plug in. One half. 5 over 4 times 5 pi over 3 plus 1/4 sine of 10 pi over 3 minus 2 sine of 5 pi over 3 minus, and then we plug the other one in, 5 pi over 3 times 5 over 4 times pi over 3 plus 1 over 4 times the sine of 2 pi over 3 minus 2 sine pi over 3. Ugh. I know, this one's a icky one. I probably myself would have gone from pi over 3 to pi and double it. That's what I would do. Because then I would get signs of pi's in here, which would cancel things out. But that's okay. That's okay. So yeah, I'll just put a little note that in my thought bubble, if I was doing this problem, I would double this measure 1/2 from pi over 3 to pi, and then I would do the same thing inside. That's how I would have evaluated that sucker. Because that would cancel. It would just make it nice and cleaner. But that's okay. Here we go. So underneath we get 25 pi over 12 plus 1/4 times sine of 10 pi over 3. So now I have to figure out where 10 pi over 3 is. 10 pi over 3 is 3 1/3 pi. So that puts me down here. And the sine is negative square root 3 over 2. Sine of 5 pi over 3 is also negative square root 3 over 2. Sine of 2 pi is positive square root 3 over 2. Positive square root 3 over 2. Ugh. So that gives me 2 square root 3's over 2 square root 3's from this piece and this piece. It gives me 20 pi over 12 from this piece and this piece. And then I got, what do I got in the middle? Minus 1/8 minus 1/8 gives me minus 2/8, which is minus 1/4 square root of 3. And that's from the other pieces. Ugh, I hope this is the right answer. Are you guys getting something like this? I'm getting something just incredibly icky. I got 5 pi over 6. Nope, over 3. Minus square root 3 over 4 plus 2 square root of 3, all of that times 1/2. I would now go check on Desmos and make sure I got an equal answer there.
On the test, if we're running low on time,
Yeah,
we just leave it like the 1/2 5/4 times 5 pi over 3.
that's fine. That's fine.
So if I
Absolutely.
was later.
Absolutely.
So if you did do the pi, the 3 pi over, the pi over 3 to pi,
Pi, yes.
yeah, that would be,
Yes.
just what's in there, that 1/2.
It would give you a lot nicer because then it would be
Yeah.
pi over 3 to pi. That would give me this guy, right?
Yeah.
And on top of that, it would, which gives me close to this. Not quite the same thing. But I've got a half in front. And then I wouldn't have the half in front. But then I have 0, right? So I would have, so then the sine of 2 pi is 0, sine of pi is 0. So then I would get the same thing, except I would have an extra 5/4 pi, and I would add 5/4 pi to that, which would give me 15 minus 5, 10. I would have 10 pi over 12, which would come down to 5 pi over 6.
Yeah.
I wouldn't have the half out front. Here I get it here. That would work.
Yeah, it would be 5 pi over 6.
Yes,
And
it
the rest
would
of
be.
it's the same, right?
Yes, it would be. It would be very nice. Yes, it would come out okay.
That's what I get.
Well, you wouldn't get twice as many here and here, but that would cancel with the half.
Yeah.
Yes, yes.
So I get minus 3 over 4.
Yep.
or 3 over
Yep.
4,
Yep.
plus 3 over 3.
Yep.
Another problem.
Yeah, you want to do one more problem? Do you want to do one more area, or do you want to save area and look at the arc length formula?
That's not an arc line.
Let's look at arc length formula. How about we look at the arc length formula? Then we'll warm up with the area. Okay. Let's look at the arc length formula. So I could do the math. We can do the math if we want to. Let's talk about arc length. So going back, if we were to talk about parametric curves, if you look back in your notes, you would see that the arc length for a parametric curve means as you're tracing this curve in space, right, as you're going along in space, starting at t equals alpha and finishing at t equals beta, there's a certain length to that curve. And that length is measured by little lengths, which we broke up into Pythagorean theorem. We did our formula, and so this was our formula. dx dt squared plus dy dt squared with respect to t gave us the arc length of a parametric curve. If we were to go through the math like we did for getting dy dx, and we remember that each curve x is r of theta, function of theta times cos, y is r times sine, we could then go on, find dx dt, dy dt, do all the algebra. So we would go through and do all the algebra, and this is the formula that would result if we did all that algebra out. Do simplifications. Do you want to do the algebra out, or are you okay if I just give you the formula and then we use it? Yeah, okay. All right. I mean, I'd love to do it, but it's just algebra. So we're going to skip the do it out, but the way to get there is you take these and you would find dx d theta, you would find dy d theta, and then you would plug those in, and that's how you would get this formula here. But it turns out that if you want to compute the arc length from theta equals A to theta equals B, or again, I like to use, and I need to update my notes, I like to use alpha and beta. Those are my variables when I talk about angles measures. So I'm going to go from alpha to beta. Of the square root of r squared plus dr d theta squared d theta. So the length of a curve from alpha to beta, or from angle alpha to beta, is going to be r of theta squared, your radius squared, or your r function squared, plus the derivative of r with respect to theta squared d theta. This is the arc length of a polar curve. So we want to set up the integral to find the length around the entire cardioid, r equals cosine theta. And so I better go to Desmos and see how long does it take me to get around that curve. So if I go over to Desmos, so we're going to do r equals 1 plus cosine theta. R equals 1 plus cosine of theta. And I'm going to type this into Desmos. Do you guys see this? It's this heart shape, right? But Desmos tells me, right here, if you look up underneath the function, Desmos tells me it's really faint, but it tells me how long it takes me to get around this entire curve. 0 to 2 pi. So when you're talking about the arc length all the way around, it's going to go 0 to 2 pi. What was that? Sorry.
I was asking you to plug those in for the limits.
Yep, those are my limits. Yep, so we got this curve.
And in this case, that's also where it's equal to 0.
Yes, it is, isn't it? Isn't that cool? Yep. Actually, when theta is 0, yep, so what we're really doing is theta equals 0, and then we're going around. So right here at pi, it's there, and then going around again, so theta equals pi, and then over here, theta equals 2 pi. To get...
Still have decimals.
Oh, you guys can't see that. Sorry. No wonder you're looking at me like I'm crazy. Sorry. So here I am writing it over here, and yeah. So 0 is over here, and then you, thanks Drew, and then you go here at pi, and then you go back over here at 2 pi. So to go the entire length of that curve, we're going to go 0 to 2 pi, right? And then we're going to put into it the square root of, and then we need to put our function right here, which is going to be 1 plus cosine theta. And then we're going to put our derivative, which is dr d theta, which is the derivative of 1 plus cosine theta. Are you guys getting minus sine theta? Oh, this is so easy and so quick, huh? When we expand that out, that gives us 1 plus 2 cosine theta plus cosine squared theta plus sine squared theta d theta.
It doesn't cosine squared plus sine squared. Yeah. It's 1.
Oh my goodness gracious. Okay. Arg, blarg, jarg, derg, gur, gur, gur.
So if it goes the full way around like that, will it always be 0 to 2 pi for the
Mm-hmm.
Okay.
Mm-hmm.
Yeah, because 2 pi, you'll get the unit circles all the way back around.
Yeah.
All right, guys. Dang it, dang it. Oh, good. We have a little bit of time to talk about this. Ay, 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 ay. We have done one of these this semester, I believe.